t distribution. So it's the mean plus or minus the critical value of the t statistic times the standard error, which is the standard deviation over square root of n. I use the t distribution, not the normal distribution here, because I estimated the standard deviation from this sample. And then I could have used this table here to look up the values. Remember, it would have been plus or minus 1.96 standard errors for the normal distribution, but we were using the t distribution with 22 and minus 1 degrees of freedom. Let's see, for two tails at 0.05, it's right here, 2.07. So for alpha equals 0.05, 22 degrees of freedom, it's 2.07. For the other one, alpha equals 0.5, that's not actually shown in the table, so I used software to calculate it, and it's 0.69. And the ratio of those two is 3. That's how I put that red line on the plot there. So I could ask you something like, how much bigger should a 95% confidence interval be than an 80% confidence interval? And you could answer that just by looking up in this table what the difference in the ratio of those t statistics is. So key points here on confidence intervals before we move on to hypothesis testing. Is remembering that relationship between the sampling distribution and the confidence interval, how we use the sampling distribution, whether it is the normal distribution or a t distribution, to calculate confidence intervals. You have equations for that. The interpretation of the confidence intervals, remembering that it's a plausible interval in which we have a certain probability of it containing the true population mean, or alternatively, if we were to take a bunch of samples, it's the percentage of time that that the calculated confidence intervals would contain the true mean. And of course, putting that together and actually estimating confidence intervals from data. Any more questions about confidence intervals? We're going to move on to hypothesis testing now. Yes? Yes, we use the t statistic when we're estimating the standard deviation from the sample. Oh, if your sample size is greater than, say, 300, then there's basically no difference between the t distribution and the normal distribution. There is still a difference. If you wanted like a 99.9% confidence interval, the t distribution is still the correct one to use. But for something like a 95% confidence interval, I don't have the rest of the table on here, but if you look up at like n equals 300, then this 2.04 here would be down to pretty close to 1.96, which is what you get from the normal distribution. So I wouldn't really worry about that n greater than 300, because the t distribution is always correct when you're estimating the standard deviation from the sample. In any case, we're assuming that it's drawn from a normally distributed population. And then there was the other sample size thing that I gave you, the n greater than 30. That was for central limit theorem kicking in and it not mattering so much whether the population is normally distributed.
So,
yeah.
If we have the mean of the standard deviation of the population, we don't have to use TS2.
Right. If you have the standard deviation from the population so that you don't have to estimate it from the sample, then you're going to use the normal distribution, no t-distribution. The reason for the t-distribution is that when you estimate the standard deviation from the sample, you start by estimating the mean, and you put the estimated mean in the place that minimizes your standard deviation, and that introduces a bias. It's an underestimate of your standard deviation. Like if you have a sample of 3 and you get 3 measurements like this, you're going to estimate the mean to be right there, which is the place that minimizes the variation from the mean, even though the true mean probably isn't right there. Yes? Does having a small sample size have anything to do with using the t-test? Yes, in that the smaller your sample size, the more the t-distribution diverges from the normal distribution. So the more important it is to use the t-distribution. If you had n greater than 300, you would never notice the difference, whether you use t or normal distribution. And you can kind of see that here, looking at your multiplying factor for the 95% confidence interval as you decrease the sample size. Here where we were at 22 degrees of freedom, the critical value of t is 2.07, but if we go down to 1 degree of freedom, so it's estimated from a sample of size n equals 2, then that confidence interval, what we multiply the standard error by, goes up to 12.71. So the smaller the sample, the more it matters that you use the t-distribution. Mm-hmm.
Say, for example, you have the value of mean, confidence.
Sorry, a value of what?
Okay, let's say you estimate the 95% confidence interval.
Mm-hmm.
You have a range. As long as the mean is in that range, you can say that that's a correct value.
Okay, so the question was, if you estimate a 95% confidence interval and you find that the mean is in that range, then it's a correct value. So are you talking about the population mean or the sample mean?
I guess it would be the sample mean.
So the sample mean, by definition, lies in the center of your confidence interval. So just by the way we calculate the confidence interval, it's centered at the sample mean, and it goes up and down by our margin of error. So that doesn't, I mean, yes, it has to be within there for your confidence interval to be correct, but as long as you don't make a mistake in your calculations, it will be.
What is the borderline?
So if the true population mean lies outside of that 95% confidence interval, that's going to be what we're going to call a type 1 error in hypothesis testing. That does mean that you've made an error in your estimation. You know, you've admitted that you have some uncertainty, but still you said, I think it's in this interval, and you're wrong. And that is a type 1 error.
The population mean is not in that interval.
Right. Wrong. Right. It's wrong. Yeah. Yeah. The goal is that if your calculations and your sampling are done correctly, then 19 times out of 20, your 95% confidence interval will be correct. But 1 time out of 20, it will be wrong. And you expect that 1 time out of 20. If you're actually right 99 times out of 100, then that's not a good 95% confidence interval. What do you mean by a close call?
Like I think we had a question with
Uh-huh.
I can't remember exactly, but
A close call is in a true mean that is right kind of on the edge.
yeah.
Yeah.
Then
right.
we are confident on the edge.
So that just, a priori, you're going to make the decision on alpha, your type 1 error rate, and you're going to make your decision based on which side of, your confidence interval or your critical value of the test statistic it lies on, and it's just going to be a black or white yes or no, regardless of whether it's on the edge or not. However, you should recognize that that border is somewhat arbitrary, and having something fall on just one side or the other, you should recognize that if you were to take another sample using exactly the same methods, you would get a different interval and you might make a different decision. So it's just a matter of understanding that these values are random. They're from a random sample. And even if you don't make your conclusion at 95% confidence, there might still be some evidence for something that you're observing. So yeah, and if it's exactly on the border, it's kind of a funny question, but by tradition, that would not be included, as the borders are not included. Like you say, p less than 0.05, not p less than or equal to 0.05, but it doesn't happen in practice. So. Any more questions? I'm happy to keep talking about this. This is very important, so I want everyone to be clear on it. All right, so we have confidence intervals, which are a nice way of expressing uncertainty. So why would we want to do hypothesis testing? And we do hypothesis testing when we want to answer yes/no questions. For example, does a population mean have some hypothesized value where the answer is going to be yes or no? Whether an intervention causes some effect relative to a control group. For example, do hypertensive smoking men have the same mean cholesterol level as the general population? That'd be an example of the first one. Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? That would be an example of the latter. So these are questions that are of public health interest and to which we would like to make a yes/no answer to. That's where hypothesis testing comes in. This latter one is an actual example that I posted the article for you on Blackboard, and I think this is kind of an interesting example just because the methods are beyond anything you're going to cover in this class. It's a cluster randomized trial. They calculate adjusted risk ratios. However, the results, everything in this abstract are things that you're learning about in this class, so you should be able to interpret really all of the important results from this paper. They include confidence intervals, p-values, and they go on to make recommendations on a public health issue. And this is probably a little bit too small for you to read up on the screen. I don't know if you can see it on your handouts, but I'll just summarize the main thrust of this paper is an intermittent screening and treatment program of schools in, what was it, Kenya? Yes, south coast of Kenya, where there were control schools where nothing was done, and treatment schools where an intermittent treatment and screening program for malaria was introduced. And then the outcome measures were anemia and certain educational achievements. And the conclusions of the paper is that no effect was observed on either of these outcomes, and they gave p-values and confidence intervals on the risk ratios for students in the treatment and in the control groups. So the idea behind hypothesis testing is that we're going to take observations and hypothesize that they come from one of two population distributions, where one of them is the usual one that has been true in the past or is observed in a control group, and the other one is a potentially new distribution that we hypothesize based on an intervention or this group being in some way potentially different from the usual. And the classic example that you'll read in many statistics test books about what hypothesis testing is about is you take a handful of beans and see that a few of them are that most of them are not white, but you look in this bag and most of them are white, so probably this handful of beans didn't come from that bag. So you don't have complete, you're not counting all of the beans in the bag, you're just looking at these few beans in your hand and saying it probably didn't come from that bag. Another classic analogy is the courtroom trial, where the defendant is considered not guilty until guilt is proven, and that is the analogous to what we're going to call the null hypothesis, or H0. And then your prosecutor tries to prove the guilt of the defendant, and that will, or to prove the guilt of the defendant, that we'll call the alternative hypothesis, HA or H1. And we accept that alternative hypothesis only when there is enough evidence to reject H0. If there is a lack of evidence, then we accept H0, or we accept the innocence of the defendant. And this little table summarizes for you the types of errors that can occur in the hypothesis testing framework. So if your null hypothesis is true, the defendant didn't do it, then if you make an acquittal by accepting the null hypothesis, that's the right decision. If you make a mistake, you reject the null hypothesis and convict the defendant, that's a type 1 error. And that's the type of error that we're going to be controlling with the p-value. And then alternatively, if the defendant is actually guilty, but you acquit that defendant and let them go free, that's a type 2 error. So failing to gather the evidence to reject an incorrect null hypothesis. And of course, if H1 is true and you reject the null hypothesis, then that's a right decision. So there's a nice analogy between confidence intervals and hypothesis testing. It's very intuitively appealing, and so intuitively appealing that it sometimes gets abused, as I'll tell you later. But in the context of one sample, as we're covering today, it is very intuitive. So when you create your 95% confidence interval, you're giving a region where 95% of the means in your sampling distribution lie. And 5% of the probability in your sampling distribution lies in the tails out here. So you've got, 2.5%, and I've got it written there, 2.5% in each tail. So if you are constructing a confidence interval, you put the middle of it right here in your sampling distribution, and you put the edges of it right there. And if it is, you're using a normal distribution, it's at plus or minus 1.96 on the scale of the z-score. And alternatively, if we're thinking of this as a hypothesis test, so in the confidence interval, we set z equal 0 where the sample mean lies and put the intervals at plus or minus the sample mean. In the hypothesis test, z equals 0 corresponds to the theoretical mean under the null hypothesis, and then we'll calculate z for our sample. And if that value of z falls somewhere outside in these tails, then we'll reject our null hypothesis. Looks like there's a question. Uh-oh, the video froze for me. Let's see. I'm just going to try starting it again. I hope that's better. Let me know if it's still frozen. Okay, so mathematically, there's this kind of equivalence but slightly different approach that you would use for confidence intervals and for the hypothesis test. In practice, if you calculate your confidence interval and the hypothesized value under the null hypothesis falls within that confidence interval, then you don't reject H0. If it falls outside the interval, you do. So in the confidence interval framework, it's where does your sample mean? Does the H0 value fall within your confidence interval? And within the hypothesis testing mean, does your test statistic fall within the critical values of your test statistic? Any questions about that? Yes? Yeah, why don't I draw it? I feel like that might be easier here. If on the age one, we put a 95% confidence interval between, well, actually I have an example of this. I'll do it anyways now. But between, say, 38 and 48, and H0 is that mu equals 36, and you're going to reject your null hypothesis based on your confidence interval because your hypothesized value lies outside of the confidence interval. I'm going to lay out hypothesis testing for you in 5 prescribed steps. Just as you do this over and over, you might be less formal about it than this, but it is really worth at least thinking through these steps, especially as you're getting started, because your software is just going to spit out an answer to you. But unless you're clear about some things like what your null and alternative hypotheses are, you might misinterpret those results. And there are some classic ways that you can get tripped up by not being clear about your null and alternative hypotheses. I think the video is frozen. Keep repeating a small segment. Uh-oh. Well, you're seeing the same thing that they're seeing online. So I don't think it's a problem with the Hangout because no one in class would be able to see it either. So I think it might be a problem Amanda, with your internet connection. But you should be able, it'll be recorded, you should be able to watch it later still. Yeah, it continues to buffer. I suspect that you're having problems with the internet connection. So step 1, state your null and alternative hypotheses. Step 2, specify the significance level in a paper. That will often get done in the methods. Step 3 is to go ahead and draw your sample of size n and compute a test statistic according to the rules we've learned. Then you determine your p-value. I might add to this or critical value of test statistic. When you're using software, you're just going to compute a p-value. But sometimes it's interesting to use a table, and we've done some examples using the tables. And if it's a table of t-values, you're probably not going to be able to calculate an exact p-value, but you can calculate your critical value of the test statistic. That will help you decide whether your test statistic is outside of, in those tails, beyond the critical region. And then you compare your p-value or your test statistic, the p-value to the significance level alpha or test statistic to the critical value, and then state whether or not you reject H0 and write down your conclusions in terms of the subject matter, like your conclusions. Let's have a little bit more detail about this. So formulating the null and alternative hypothesis. Again, the null is the no difference. It's the thing that you're going to accept in the absence of sufficient evidence. So that there is no effectiveness of a treatment, that the population you're observing is no different than some other population. That's your null hypothesis. And then your alternative hypothesis will be that there is a difference. And we'll explicitly write some of those out later. And I will be encouraging you to write them out as an actual formula. So again, the alternative hypothesis is that there is some difference between the distribution you're observing and some previously known distribution. And if the null hypothesis is unlikely given your data, then you're going to accept the alternative hypothesis. So if you, your null hypothesis is that your beans came from the bag of mostly white beans, but your sample has mostly black beans, you're going to reject that null hypothesis. Two-sided alternatives, we call them two-sided because the difference from the null hypothesis could be something either greater or less than the null value. And we write these down as follows. So H0, that's the null hypothesis. The colon, that's just kind of a standard for writing what follows this is my null hypothesis, is that the mean of the population from which we're sampling is equal to mu naught, a hypothesized mean. And the alternative in the two-sided case would be that the mean is not equal. So it might be greater, it might be less. For example, is the blood pressure of smoking males the same as the general population? If the general population is 211 milligrams per 100 mLs, this is how you would write out your null hypothesis and your alternative hypothesis. In the example of that paper where they were, one of the outcome measures was the prevalence of anemia in school children. So that's that you're talking about a proportion. Their null hypothesis was that the prevalence in the control group was equal to the prevalence in the treatment group. And their alternative, a two-sided alternative, was that the prevalence was different between the control and treatment groups. So you notice, even though presumably they did the trial because they thought that maybe the treatment would decrease the prevalence of anemia, that's not their alternative hypothesis. It's a two-sided hypothesis, which is the norm, the standard. I'll tell you later a little more about why that is, but very rarely are you going to use a one-sided alternative hypothesis. But so you know about them. They have an inequality in them. So the null hypothesis still must include the equality. You'll notice that the null here is that the mean is less than or equal to the population mean. So this equality has to be included. The no difference possibility has to be included in the null hypothesis, not the alternative. But the alternative hypothesis here is just that the mean is greater than the hypothesized value. And it's similar for the mean of two samples. Again, the equality is included in the null hypothesis. But note that equality could be in either direction. So you could also have a null hypothesis where mu1 is greater than or equal to mu2. But the two key points here are that 1, H0 includes the equality, and 2, H0 plus HA include all possibilities. And 3, there is an inequality. For the one-sided scenario. All right. So that choice depends on the context of the problem, but one-sided tests have to be very well justified, because in general you can get a p-value that's half of what you would get from a two-sided test, as long as your hypothesized alternative was in the right direction. So there should be no reasonable possibility of the other inequality happening, or it's just because the objective of your study is to show, for example, that a treatment is not worse than the control group. So it just has to be very well justified in advance of doing your study. Choosing your significance level, it's usually 0.05. In almost all public health literature, it's 0.05, even though that's an arbitrary value. But if you choose something else, people might want to know why you chose something else. That will affect your trade-off between type 1 and type 2 errors. So you may want to choose something else if your relative importance of a type 1 error or a type 2 error is different. If you are very concerned about acquitting guilty prisoners, then you should set a very small alpha, like 0.001. If you're more concerned about releasing a guilty prisoner or releasing a guilty person, then you would set a higher value of alpha, maybe 0.1, 0.2, 0.3, but then you're more likely to convict an innocent defendant. Yes?
In the problem, how do we know if we have to choose one side or two sides?
Mm-hmm.
Only with the instructions of population, we know which.
How do you know whether to choose a one-sided or a two-sided? Do you mean out in the world or like on an assignment or exam?
What is the assignment that we got?
Yeah. It will be made abundantly clear to you if you should choose a one-sided test. Like, it will be, the equality will be clear from the way the question is worded. So once again, alpha is referred to as the type 1 error rate. That's very important. Step 3, you already know how to calculate your Z statistic and your T statistic. So I won't go over that. We're getting a bit short on time here, so I'm going to skip by a couple of slides. On calculating the p-value, just to summarize this slide, the p-value is calculated on the presumption that your null hypothesis is true. You're calculating the probability of drawing a sample with the mean that you observed or something more extreme. That is your interpretation, or that is the mathematics of the calculation of a p-value. So it's done under the assumption that the null hypothesis is true. What's the probability of observing your sample or something more extreme? All right, and finally, based on your p-value or your test statistic, you either accept or reject the null hypothesis. All right, so here we have one more example that I want to go over, and this one's, but I encourage you to read this over and ask yourself these questions and post to the to our Google group if you're not sure about any of the answers, asking what is the outcome variable, what are the null and alternative hypotheses, the significance level, the p-value, and whether or not H0 was rejected, why they made that decision, and how they reported it. These are kind of, you can see all of the steps of hypothesis testing in this abstract.